morning, dear students. Today is the lecture number 10 on the topic of linear programming. We will be talking about the two cases, that is the infeasible solution case and the degenerate solution case. The outline of today's lecture is as follows. We will study the infeasible solution case with the help of the graphical method as well as the simplex method to see a comparative analysis of the situation when we have a infeasible solution. Next, we will talk about what do we mean by a degenerate solution. Then we will be talking about a situation where instead of having non-negativity constraints as the decision variables, we have the variables as unrestricted variables in sign. Unrestricted means unrestricted in sign. Next, I will be telling you about some important tips, and then I will give you a short answer type quiz, and finally some homework and exercise. So, let us start with the help of this example. Here again we have a two variable problem which is to be maximized, and the objective function is 5x1 minus x2 subject to 2x1 plus 3x2 less than or equal to 6, 5x1 plus 4x2 greater than or equal to 20, and both the decision variables x1 and x2 should be greater than or equal to 0. So, first of all, as before, we will use the graphical method to solve this problem. So, on the xy axis, here is the first line that is representing the constraint, the first constraint, and then we want to see which side of this line does the feasible domain lie. And as you can substitute the value of the origin in the inequality, you find that the feasible region should be below the line. Next, we plot the second constraint and again substitute the origin into the inequality to see if which side of the line does the feasible region lie, and we find that the feasible region lies above the line. So, what does it mean? It means that there is no common area which we can call as the feasible region, and therefore, this indicates that the problem has no feasible solution. As you can see, the coordinates of the points which intersect with the line and the x axis and the y axis are indicated as A, B, C and D, but there is no feasible solution, and this is what we are concerned with when we have no feasible solution. It is also called a infeasible solution case. So, we will solve this very problem with the help of the simplex method, and we will identify what happens in the calculations of the simplex method, so that we can identify that the problem has a infeasible solution. So, as before, I have written the problem again, that is we have a two variable problem which is to be maximized 5x1 minus x2 subject to twice x1 plus 3x2 less than or equal to 6, and 5x1 plus 4x2 should be greater than or equal to 20. So, we will first of all write the problem in the standard form, and we will make sure that every constraint has a basic variable. So, what will happen in the first constraint, we will introduce x3 which is a slack variable, and in the second constraint we will introduce x4 which is a surplus variable and it has to be subtracted. And since there is no basic variable in the second constraint, so we need to add a artificial variable in the second constraint. This means that the problem becomes a 5 variable problem and we will solve it with the help of the two phase method. So, the first phase of the method means that we have to minimize the sum of the artificial variables. Now, as you know that there is only one artificial variable and we want to maximize minus of this artificial variable, that is maximization of minus x5, and the constraints are as it is. So, we will put all this information in the form of a table. As you can see that in the first equation the basic variable was x3. So, x3 and x5 come under this column of basis and its corresponding coefficients in the objective function, that is 0 and minus 1. I hope you remember that during the two phase method we set aside the original objective function and replace it with a temporary objective function. So, the constraints of the objective function are as follows: 0, 0, 0, 0 and minus 1. Under the x1 column we have 2 and 5. So, these are the entries under the x1 column. Under the x2 column we have the entries 3 and 4. Under the x3 entry we have 1 and 0, and x4 we have 0 and minus 1, x5 we have 0 and 1, and the right hand side is 6 and 20. So, this is the initial table that we have constructed, and the next thing we need to calculate is the deviation rows. So, the deviation rows are calculated as before: 0 minus 0 minus 1 multiplied by 2 5, and the answer comes to be 5. Similarly, 0 minus 1 multiplied by 3 4, the answer comes to be 4. Now, x3 is a basic variable, so its entry in the deviation row is 0, and similarly the x5 variable is also a basic variable, so its entry also is 0. Only x4 will be different and it is 0 minus 1 multiplied by 0 minus 1, and that comes out to be minus 1. Now, the objective function value for this modified objective function is minus 20, and therefore, we can say that the BFS is as follows, that is x3 is equal to 6 and x5 is equal to 20 and all other variables as 0. So, we will decide which variable should enter the basis, and for this we look at all the entries in this deviation row, and the highest entry as you can see is 5. So, this indicates that this variable x1 should enter the basis. So, the entering variable is x1. Then we will perform the minimum ratio test, 6 divided by 2 and 20 divided by 5. Which one of them is the minimum? The first one is the minimum, and this indicates that x3 should leave the basis. So, the decision is that the leaving variable should be x3, and this tells us that the pivot should be 2, which is shown in the pink color. So, 2 is the pivot and we have to apply the elementary row operations in such a way that this 2 becomes 1 and this 5 becomes 0. You see, then only x1 will become a basic variable. So, what are the elementary row operations that we should apply? First of all, we should multiply the entire first row with 1 by 2, or rather we should divide the entire row 1 with 2. So, once you apply this, you will get this pivot will become 1, and that is what you want. Apart from this, we also need to apply this elementary row operation, that is R2 minus, R2 should be replaced by R2 minus 5 times R1, because if you apply this elementary row operation, then this entry over here under the x1 column will become 0. So, and that is what you want. So, by applying these elementary row operations, this is what you get. The first one was divided by 2. So, this becomes 1, this becomes 3 by 2, this becomes 1 by 2, 0, 0 and 3. So, this is the first row. Next, we apply the second elementary row operation on the second row, and what is that? That is R2 should be replaced by R2 minus 5 R1, and that makes this entry as 0, minus 7 by 2, minus 5 by 2, minus 1, 1 and 5. So, this gives us the second table of the phase 1, and as before, we will now calculate the entries in the deviation rows. Now, you will observe that since x1 is a basic variable, so the entry corresponding to this x1 should be 0. Similarly, since x5 is also a basic variable, so the entry corresponding to x5 should also be 0, whereas the other ones we need to calculate. So, for x2 we have 0 minus 0 minus 1 multiplied by 3 by 2 minus 7 by 2, which comes out to be minus 7 by 2. Similarly, 0 minus 0 minus 1, 1 by 2 minus 5 by 2, and this comes out to be minus 5 by 2. And similarly, for x4, 0 minus 0 minus 1 multiplied by 0 minus 1, and that gives you minus 1. So, what we find is that we have got all the entries of the deviation row. Now, what we find? We find that the stopping criteria is satisfied. Why is it the stopping criteria satisfied? Because all the entries in this deviation row are either 0 or negative, and that is what is the stopping criteria of the two phase method or the simplex method. That is, all entries in the deviation row should be either 0 or should be negative. Then that means that optimality has been attained and no further improvement in the objective function is possible. So, we find that the optimality condition has been satisfied. But if you look carefully, what do we find? We find that this artificial variable x5 is still in the basis, because our artificial variable x5 is having value 5, and our first phase of the objective function is still not attained. So, this means that since the artificial variable has not been eliminated from the basis, it means that the problem of this LPP is having no feasible solution. So, this is what we conclude: no feasible solution exists for this particular LPP because the artificial variable x5 is still in the basis, it is still non-zero. See, ideally we should have had this become 0, but unfortunately this has still non-zero. So, this is an indication that the problem has a infeasible solution. Therefore, what do we conclude? We conclude the following, that the condition for an LPP to have a infeasible solution is if the optimality is achieved, that is the optimum solution has been achieved, but the artificial variable is still in the basis, that is it is non-zero. Still in the basis means it is still non-zero. This is the condition which we were looking for, that is for the infeasible solution the artificial variable have a value which is greater than 0. So, next let us look at the degenerate case. Now, if you look at this problem carefully, we have maximization of 5x1 plus 3x2 subject to x1 plus x2 less than or equal to 5, 3x1 plus 8x2 less than or equal to 24, 9x1 plus 34x2 less than or equal to 90, and x1 and x2 greater than or equal to 0. So, this looks quite a normal kind of an LPP, but when you try to plot this LPP onto the two-dimensional space, you will find that it has a specific nature, and that is what we are going to do. So, the condition which are satisfied for a degenerate solution are as follows. This happens when three constraints pass through a vertex of the feasible domain, and the corresponding condition in the simplex calculation is that if a 0 appears in the right hand side of the constraints. So, these are the two vis-a-vis conditions for the graphical method and the simplex method. So, let us try to draw the graph of this problem. First of all, the first constraint, it passes through the point 0, 5 and 5, 0. So, these are the 2 points. The area of the feasible region is below the curve. So, this is indicated by the arrow. Next, we will plot the second constraint. This passes through the 2 points A given by 0, 3 and the point 8, 0, and the arrow indicates that the feasible domain is below the line. Also, the third constraint also passes through this point and the feasible domain is below the line. These are the coordinates of the feasible region: A given by B, C and D. So, we can shade the feasible region as follows, and this indicates that the feasible region has these vertices A, B and C. And also we find that the solution of the LPP lies on this point B, and you can see that instead of 2 lines there are 3 lines which are passing through this point B. This is an indication that this particular problem has a degenerate solution. As far as the conditions in the simplex calculation is concerned, I mentioned that it is that in the right hand side if we get a 0, that is an indication of the degenerate solution. So, next now let us look at a situation where we have unrestricted variables. Unrestricted means unrestricted in sign, that is they are not necessarily greater than or equal to 0. It is not specified that they are greater than or equal to 0. They may or may not be greater than or equal to 0. So, if there is a variable x which is a variable which is unrestricted in sign, then the trick that has to be applied is to represent it as the difference of 2 variables which are both positive. So, here is an example. Suppose we have x is a variable which is unrestricted in sign, then we will write x in terms of x dash minus x double dash, and once we write this we have to make sure that x dash should also be greater than or equal to 0 and x double dash should also be greater than or equal to 0. But with this substitution, this has to be made in the entire problem, not only in the objective function, but also in the constraints, and then solve the problem as usual. Of course, the number of decision variables will increase by 1, because now instead of x we have substituted x as x dash minus x double dash. That means one more variable has increased, and obviously you need to use the simplex method to solve this problem. So, I hope that this condition has been understood. Now, some important tips when you solve exercises on the various conditions of the linear programming case. The first one is that in case there is a tie between the largest deviation in the deviation row, largest entry in the deviation row, then the choice has to be made according to the least subscript. That is, if there are two variables, for example x1 and x6, both of them are having the same entry corresponding to the deviation row, the entry is equal and it is not possible to decide which one should be allowed to enter into the basis. In that situation, it is important to make the variable which is having lower subscript, that is, if x1 and x5 are there, then choose the one corresponding to x1. Although if you choose the other one, you will also get the answer, but probably the number of iterations might be more. So, in case of a tie, choose the one with the lower subscript. Similar situation might arise when there is a tie between the minimum ratio test, that is, the minimum ratio test is equal for corresponding to two rows. Again, in this case you can choose at random, although the solution will be the same, but the number of iterations might vary. So, the solution of a LPP can be used to solve many kind of problem arising in mathematics. As an example, I am taking the solution of a system of equations which we will be forming as an LPP, and then we will use the simplex method to solve this system of equations. So, let us see how this has to be done. As an example, let us suppose that we have to solve the following system of equations, which is two equations in two unknowns. So, we have twice x1 plus 3y is equal to 8, and the second one is 3x minus y is equal to 1. Now, let us suppose that it is given that x and y are both greater than or equal to 0. If these non-negativity conditions are not given, then we can consider that x and y are unrestricted variables and replace both these variables as a difference of two other non-negative variables and substitute in the two given equations and then solve as before. So, let us see what happens if we use the two phase method. We will maximize the artificial variables that have to be imposed into the both these equations. So, in the first equation we will add an artificial variable x3, and in the second equation we will add an artificial variable x4. This means that now we have a 4 variable problem and all the variables should be greater than or equal to 0, and x1 and x1 and x2 are the two artificial variables. Now the phase 1 will be completed. When the phase 1 is completed, then we will find that all the artificial variables have disappeared, provided the solution has, the system of equation has a solution, because if it does not have a solution, then it will indicate that there is no solution to the problem. But if the system has a solution, then we will get at the end of the phase 1 we will get all the artificial variables will disappear. So, this lecture is the concluding part of this particular section of this course on linear programming, and therefore, in order to recapitulate what we have learned in this series of 10 lectures, I would like to give you a quiz which is based on short answers or based on what we have studied. I want you to understand and write the answer to the quiz as and how we proceed. So, here comes the first question. Please write down the answer in your notebooks. The first question is, the feasible domain of a linear programming problem may or may not be bounded. The answer is either true or false. So, if you think it is true, please write true in your copies. If you think it is false, please write false in your copies. The second question, the feasible region of a LPP is always a convex set. Again, the answer is either true or false. Please write down the answer in your booklets. The third question, dash variables are added to make less than inequality into an equality. Dash variables are added to make less than inequality into a equality. Now, you have to write down the name of that variable. What is the name of that variable? The fourth question, the optimal solution obtained by the big M method is never unique. The optimum solution obtained by the big M method is never unique. The answer is either true or false. You remember, we have been talking about unique solutions and multiple solutions. So, the question is, the optimum solution obtained by the big M method is never unique, true or false? Then comes the fifth question, the two phase method is applied when something is not readily available. So, that is something you have to fill. The two phase method is applied when a dash is not readily available. It has a specific name. I want you to write that name, that particular name. What is not available? Why is the two phased method applied when something is not available? Okay, the sixth question, in a LPP, if one of the coefficients in the deviation row corresponding to the non-basic variable becomes 0, then the problem has unbounded solution. If a LPP if one of the coefficients in the deviation rows corresponding to the non-basic variable becomes 0, then the problem has unbounded solution. The answer is either true or false. For this you have to remember what is the condition for the unbounded solution, what is the condition for the multiple solution, and so on. So, you will get the answer if you think about those conditions. The seventh question, the optimum solution of a LPP can lie on the interior of the feasible region. So, as you have seen in the graphical method, we want to find out whether the optimum solution of a LPP can lie in the interior of the feasible region or not. So, the answer is either yes or no, or true or false. Next, the eighth question, if the minimum ratio test fails, then it can be concluded that the LPP has dash. So, if the minimum ratio test fails, then it can be concluded that the LPP has dash. Again, the answer will come if you remember all the conditions that are required for the various cases that we have discussed. The ninth question, any variable can be made a basic variable by dash. So, the dash has to be filled based upon what we have discussed, that is, any variable can be made a basic variable by applying some kind of operations. What are those operations called? So, you have to fill in that dash. Now, the 10th question is as follows, if P, Q and R are 3 solutions of a LPP, then the convex linear combination of these 3 solutions will also be a solution of the LPP. Now, this situation will arise when the problem has multiple solution. So, the question says if there are 3 solutions of an LPP, then the convex linear combination of these 3 solutions will also be a solution to the LP. True or false? Okay. So, I hope everybody has written the answers in your copies, and now I would like to give you the answers and I would like you to check whatever answers you have written in your copy. So, here are the answers to all the 10 questions that I have given you. The answer to question number 1 is true, question number 2 is true, question number 3 slack variables, question number 4 false, question number 5 basic feasible solution, question number 6 false, 7 false, 8 problem has unbounded solution, 9 by applying elementary row operations, and 10 is true. So, please check your own answers and try to have a self evaluation of how much you have learned from this part of the course and not. As an exercise, I would like to give you this question to solve later on. Solve the following LPP, show that it has no solution. So, the problem is maximization of x1 plus x2 subject to x1 plus x2 less than or equal to 1, minus 3x1 plus x2 greater than or equal to 3, x1 and x2 should both be greater than or equal to 0. So, I hope you can complete this example at the end of this lecture. Thank you.